Welcome to our online chemistry class. Presented by KHARGE from SSPMS and Junior College, Shivajinagar, Pune 5. Our topic is electrochemistry. Let us discuss part number 4 of this topic. Let us discuss electrolysis of aqueous NaCl. So in previous video also we will discuss electrolysis of molten NaCl. Here we have to discuss electrolysis of aqueous NaCl, where we use aqueous solution of NaCl and it can be carried out in the cell used for electrolysis of molten NaCl using inert electrode, and it is shown in diagram 5.4. The same diagram we have to use. Instead of fused NaCl, we use aqueous NaCl solution. So here water is involved in the electrolysis of aqueous NaCl. Therefore, the electrode reactions that differ from electrolysis of molten NaCl. So let us see first reduction. Remember that reduction always takes place at cathode. At cathode, two reduction reactions completes. One is the reduction of Na plus ion, as in case of molten NaCl. So Na plus 1 plus charge is there on aqueous Na plus ion. It accepts only one electron and get neutralized to Na solid atom. So E0 value is minus 2.71 volt. We observe the electrochemical series. In that series we observe these values for standard reduction potential. Then the another reaction is the reduction of water to hydrogen. So H2O gets ionized to H plus and OH minus ion. Okay, so here we take 2H2O and that will give 2H plus plus 2OH minus ion by gain of 2 electron. Then the 2H plus combine together to form H2 because they accept that 2 electron here. 2H plus 2 electron, H plus 1 electron gives H, 2H plus gains 2 electron gives 2 hydrogen atoms, and 2 hydrogen atom gets converted into a molecule of hydrogen, and that is in gaseous state. The OH minus remains as it is. So overall is the H plus from water gain electron and gets converted to hydrogen. 2H plus gain 2 electron gets converted to H2. So E0 value is minus 0.83 volt. Okay. So the standard potential that we observe in electrochemical series under the section of 5.7.1 for reduction of water is higher than that of reduction of sodium. So in this table 5.1, the standard aqueous electrode potential at 298 Kelvin, that is electrochemical series. So different electrodes are arranged in the decreasing order of reduction reaction. So if you observe here, sodium is here. Na plus 1 electron gives Na minus 2.714, and at the center is H, 2H plus 2 electron gives H2, and in between that there is a reduction of water. Okay, that value is not given in this table, but the value is mentioned and it is minus 0.80. So it is here, okay, minus 0.83. So this indicates that water has much greater tendency to get reduced than the Na plus ion because it is above in that series, and those elements which is present above in that series, they have more tendency to undergo reduction. Hence reaction 2, this one, that is reduction of water, is the cathode reaction when aqueous NaCl is electrolyzed. Okay, so I think all of you understood why second reaction is more preferred. Then the another reaction is oxidation reaction at anode. So at anode there will be again competition between oxidation of Cl minus ion to chlorine gas, as in case of molten NaCl the oxidation of water to oxygen gas. So first reaction is the Cl minus from that aqueous NaCl solution loses one electron and it gives chlorine atom. Another chloride ion loses one more electron to give another chlorine atom. The two chlorine atoms combine together to form a chlorine gas. That's why the reaction is 2Cl minus aqueous gives Cl2 plus 2 electron, and E0 oxidation is minus 1.36 volt. You can observe this also in that same electrochemical series. So that series is only for reduction, and if you write the reverse reaction it becomes oxidation, and the value in that table it is 1.36, but that is plus. Here we write oxidation, that's why it is written with minus sign. And another reaction is 2H2O gives oxygen plus 4H plus 2 electron, and E oxidation, that is standard oxidation potential for this reaction, is minus 0.4 volt. Now the standard electrode potential for the oxidation of water is greater than that of chloride ion, or water has a greater tendency to undergo oxidation. Therefore expected that anode half reaction would be oxidation of water, but the experiments have shown that the gas produced at the anode is chlorine and not the oxygen. This suggests that anode reaction is the oxidation of chloride ion to chlorine gas. So even though that series prefers the second reaction, our expectation is second reaction is preferred, but in experimental data we observe that the chlorine gas produced at anode, so first reaction is preferred, and the reason behind this is over voltage. What is over voltage? That is not the scope of this syllabus, but it has been found experimentally that the actual voltage required for electrolysis is greater than the calculated using standard potential, and this additional voltage required for reaction is called as over potential or over voltage. Okay, so I think all of you understood it is over voltage. So this is about the electrolysis. So what is the overall cell reaction? First one is at anode, 2Cl minus aqueous gives chlorine gas plus 2 electron, and it is oxidation because loss of electron. Second reaction is 2H2O liquid plus 2 electron gives H2 gas plus 2OH minus aqueous. So here gain of electron means reduction, and this reaction takes place at cathode. Combination of these two reactions gives 2Cl minus aqueous plus 2H2O liquid gives chlorine gas plus hydrogen gas plus 2OH minus aqueous. 2 electrons get cancelled. This is overall cell reaction. Notice the result of electrolysis. It is First, hydrogen gas liberated at cathode and chlorine gas liberated at anode. So here because Na plus ion remains unreacted and OH minus ions are formed at cathode, NaCl solution is converted into NaOH solution. We observe that there is a formation of sodium hydroxide. Okay. The next part is the quantitative aspect of electrolysis. So with the help of these formulas we can solve the numericals based on this. In old syllabus there are two laws, Faraday's first law and Faraday's second law. Okay, but in new syllabus only formulas are mentioned, so we'll discuss only that. The first one, the mass of reactant consumed or the mass of product formed at an electrode during electrolysis can be calculated by knowing the stoichiometry of the half reaction at the electrode. The first one is calculation of quantity of electricity pass. To calculate the quantity of electricity, that is Q, passed during the electrolysis, the amount of current I passed through the cell is measured. The time for which the current passes is to be noted, and then the quantity of electricity Q in coulomb is equal to I, that is current in ampere, into time in second. So that is the first formula, that is quantity of electricity is Q is equal to IT. Then second formula is calculation of moles of electron pass. So total charge pass Q in coulomb, what is the charge on 1 mole of electron? It is 96500, that is 96,500 coulombs on 1 mole of electron. So what is the moles of electron actually pass? It is equal to QC divided by 96,500 coulomb per mole. So that is the moles of electron actually pass, and the charge on 1 mole of electron is 96,500 coulomb or 1 Faraday. Okay. So when you have to calculate moles of electron actually pass, you have to take total charge pass divided by charge on 1 mole of electron. Then third one is calculation of moles of product formed. The balance equation for half reaction occurring at the electrode is derived, and the stoichiometry of half reaction indicates the moles of electron pass and moles of product form. For example, when Cu2 plus ion in aqueous solution gains 2 electrons, it gets converted to copper solid. Here 2 electrons are gained, so 2 moles of electrons are required for production of 1 mole of Cu. So here 1 is not written, but it is considered as 1. So we can calculate the moles of product form by using the previous formula. The moles of electron actually pass are given by equation 5.16, that is Q is equal to I into T. Here Q is equal to I into T. To simplify further, we introduce another formula that is called as mole ratio. And what is that? Moles of product formed in the half reaction divided by moles of electron required in the half reaction. So in this equation, 1 mole of copper solid is formed. So at numerator there is 1, and How many moles of electron required for in this half reaction? It is 2. So what is the mole ratio? It is 1 by 2 or 1 half. Then we have to calculate moles of product form is equal to moles of electron actually pass, that is given in equation 5.17, multiply by mole ratio. So what is the equation? Becomes Q in coulomb, quantity of electricity in coulomb, divided by 96,500 coulomb per mole electron, multiply by mole ratio. So what is Q? It is given in 5.16 equation. I, current in ampere, multiply by time in second, divided by 96,500 coulomb per mole electron into mole ratio. Okay. Now lastly we have to calculate the mass of that product form. So how to calculate the mass of product? It is denoted by W, moles of that product form multiplied by molecular mass. So we know that number of mole is equal to mass of that substance divided by molar mass of that substance, that is moles. So simply it is rearrangement. So what is the moles of product form? It is I in ampere into T in second divided by 96500 coulomb per mole of electron, multiply by this mole ratio into molar mass of your product. Then this is the first method. We calculate stepwise manner. Another formula in which we directly submit all the concept here that we discuss, and that is the alternative method. So let us see that one. Suppose two cells containing different electrolytes are connected in series. The same quantity of electricity is passed through them. Then the masses of the substance liberated at the electrode of the two cells are related, and it is given as follows. So mass of the substance produced at the electrode of first cell is given by, let us suppose that first substance is denoted by 1 and second substance is denoted by 2. So W1 is equal to QC, coulomb is the unit for quantity of electricity, divided by 96,500 coulomb per mole of electron into mole ratio of that first substance into molar mass of that first substance. So here Q divided by 96500 is equal to, transfer this mole ratio and molar mass of first substance to left hand side. What we get? W1 divided by mole ratio 1 into M1. Similarly, we can calculate the mass of the substance liberated at the electrode of second cell, and it is W2, and it is equal to, again, Q divided by 96,500 coulomb per mole of electron is equal to W2 into divided by mole ratio of 2 into M2. So here if you observe this equation and this one, left hand side is same, that is Q in coulomb divided by 96,500 coulomb per mole electron. So we can equalize the right hand side also. So here M1 and M2 are the molar masses of substance produced at the electrode of cell 1 and cell 2. Okay, as Q upon 96500 is same, we can compare the both equations and we get W1 upon mole ratio 1 into M1, which is equal to W2 upon mole ratio 2 into M2. That is new equation. So let us see solve numerical based on this respect. So what is the mass of Cu metal produced at the cathode during passage of 5 ampere current through copper sulfate solution for 100 minutes? Molar mass of copper is 63.5 gram per mole. So here you have to calculate mass of copper. So what is the electrolyte? CaSO4. SO4 is 2 minus, so Cu carrying 2 plus charge. So what is the equation? Cu2 plus 2 electron gives Cu solid. That is the equation. So you must able to write the correct equation. So what is the solution? So mass of Cu form, that is W is equal to I in ampere into time in second divided by 96,500 coulomb per mole electron into mole ratio into molar mass of Cu. So mole ratio is, we prepare 1 mole of Cu, and for that purpose 2 electrons are gained. So here mole ratio is 1 by 2 because 1 mole of copper is produced, and for that purpose 2 moles of electrons are required. Mole ratio is 1 by 2. Then current passed through that circuit is 5 ampere for 100 minutes. Okay, and the molar mass is 63.5. So if you substitute all these things in your formula, then you will get 5 ampere into 100 minutes. Convert that into second, because in formula we measure the time in second, and divide by 96,500 coulomb per mole electron into mole ratio is 1/2, 1 mole, and 2 mole of electrons will be produced. The molar mass is 63.5 gram per mole. Cancel the common units. Don't forget to convert. If your time is minute, convert it into second. If it is hour, convert it into second. So your answer is 9.87 gram. Okay, here we see the cancellation of common unit on numerator and denominator. Now another numerical is, how long will it take to produce 2.415 gram of Ag metal from its salt solution by passing a current of 3 ampere. Molar mass of Ag is 107.9 gram per mole. So what is the equation? So silver is the metal. You have to remember the few elements and their correct charges when they donate electrons or accept the electron. So silver is monopositive. So Ag1 plus aqueous plus 1 electron gives Ag solid. Remember that you have to write all the reactions are in reduction form. So here, to produce 1 mole of silver in solid state, 1 mole of electron will be required because Ag is 1 plus. So you must write the correct reaction. So what is the mole ratio? It is 1 by 1 because 1 electron is required to produce 1 mole of silver in solid state. Then W is equal to IT divided by 96,500 mole ratio into molar mass of Ag. So what is, so here W is given and you have to calculate how long will it take, means you have to find out the time. Okay, so you have to rearrange the equation first. So we'll see here, current is 3 ampere, molar mass is 107.9 gram per mole, and mass is given, bit of that substance is 2.415 gram of that silver and salt. So substitute the values. 2.415 gram is equal to 3 ampere into T divided by 96,500 coulomb per mole electron, and mole ratio is 1 mole per mole electron. And what is the molar mass? It is 107.9 gram per mole. So here your time in second. Okay, don't forget. So T is equal to 2.415. Transfer this denominator value to left side. So So multiply by it by 96,500, that is coulomb. Coulomb means current into time, so ampere second, you can write that unit also, divided by numerator value 3 ampere into 107.9. So answer is 720 second. So convert that into minute or keep that as it is in second, but don't forget to write the unit, that is second. We'll see one more numerical when two cells are combined together. So let us see. In a certain electrolysis experiment, 4.36 gram of zinc are deposited in one cell containing ZnSO4 solution. Calculate the mass of aluminum deposited in another cell containing AlCl3 solution connected in a series with zinc sulfate cell. Molar mass of Zn and Al are 65.4 gram per mole and 27 gram per mole respectively. So to calculate mass of aluminum. So what is the cell 1? Zinc is the electrode and ZnSO4 is the electrolyte solution. So ZnSO4, SO4 is 2 minus, so Zn carrying 2 plus charge. So Zn2 plus 2 electron gives Zn. This is the one reaction in solid state. And what is the another? AlCl3. Chloride is 1 minus, so Al is 3 plus. So what is the another cell? Al3 plus 3 electron gives Al. Okay, here the second step. Now we have to calculate the mole ratio. To prepare 1 mole of zinc, 2 electrons are required. So mole ratio for first cell is 1 by 2. Okay, and mole ratio for second cell, to prepare 1 mole of Al solid, we require 3 mole of electron. So 1 mole divided by 3 mole electron. Now the formula is W1 divided by mole ratio 1 into M1. So weight of that substance 1, that is zinc, divided by mole ratio of zinc into molar mass of zinc is equal to weight of that second cell substance, that is aluminum, divided by mole ratio of aluminum cell into molar mass of aluminum. So molar mass of first zinc is given 65.4 gram and that of aluminum is 27 gram per mole, that is M2, and mass of that zinc is given 4.36 gram. So you have to find out the W2 for aluminum. Mass of aluminum is to be calculated. It is deposited in seconds. So substitute the values. What do we get? 4.36 divided by 1 by 2 electron into 65.4 gram per mole electron, gram per mole, is equal to W2 divided by 1 divided by 3, 1/3 electron into 27 gram per mole. So W2 is equal to 4.36 into 2, this 27 transport to this side, so it goes to numerator 27 divided by 65.4, and we transfer this 3 to this side, so it goes to denominator. So your answer is 1.2 gram. Thank you for Maharashtra State Board of Secondary and Higher Secondary Education for providing the PDF file. You can watch my videos on YouTube channel KHARGE. If you like the video, you can subscribe and share. Thank you very much.